Multiple choice for lesson 28. Number 1. Must an object be rotating to have a non-zero moment of inertia? Well, what is our equation for moment of inertia? I equals the integral r squared dm. So that means that we need to know how far away we are and what our mass is. That's it. So no, motion is not required there. However, we do need to know how far away from our rotational axis we are. So we do need to know what axis we are going to rotate around, but we do not have to be moving. We don't have to be rotating. Number 2, you need to find the moment of inertia of a solid cylinder. The axis for rotation is perpendicular to the face of the cylinder, but it is not in the center of the cylinder's face like the equation sheet. What can we do? So in this case, we've got some cylinder here. Right? On our rotational axes for the equation sheet would basically go right through the center. But in this case, right, we're going to look at something that's maybe off center somewhere. So we're going to spin it around some other location. So how can we do that? There are 2 different ways we can do that. I is the integral of r squared dm, so we can always use that integration. Part B, you can use the parallel axis theorem because you have the cylinder's inertia about the center of mass on your equation sheet. So what that is telling us is that although we have the equation for I about the red axis, if we just shift that some amount, we can use the parallel axis theorem to find our new rotational inertia. So both A or B will work for that. 3. All right, so for this one, we want to figure out a way to increase the torque on the rod shown. Well, our torque equation is torque equals RF sine theta, right? So in order to increase our torque, we can increase R, we can increase F, or we can increase our sine of theta. Those are the 3 different ways that we can increase torque. So if we look at this, right, here's our R. That's how far away we are from our pivot point that the force is acting on. So do we have an option to be able to increase our radius? It says increase the angle, decrease the angle, move the force to the right, which would decrease. So we know that this one is out. That's not available. So the other 2 involve the angle because there's not one that says we can increase the force. So if we increase sine of theta is what we want to do, is there a way for us to increase or decrease the angle to change sine of theta in the appropriate direction? So let's think about this. Sine of theta basically gives us this component of our force. So if we want to increase this component, maybe we want it to be, larger in some capacity, what would we need to do in order to change our force to be this way? That means we need to increase our angle to increase that sine of theta. So theta here would have to be larger. So if we increase our angle, we will increase sine of theta. And lastly, part 4. So for part 4, we have this odd shape here, basically being pinned at the locations marked, and we want to know which of those gives us the greatest torque. from gravity. So if we assume there's our center of gravity, we've got point 1 acting right on the center of gravity. We've got point 2 acting way over here. We have point 3 acting kind of up here, and we have point 4 acting somewhere in here. We know gravity acts at the center of mass, so there's our force of gravity. Let's just zoom in so we can kind of see this a little bit better. So we want torque, and torque is equal to RF sine theta again. So we need to find the radius. The radius of the red is 0. So our torque, 0 for the red. For the yellow, there's our radius. For the blue, there's our radius all the way in. And then for the orange, there's our radius. But the other thing that we should note for the orange is that it comes out and that gives us some angle here. And so we actually have a sine of theta that's not 90 degrees for the other two, but some other angle. So that means if we were to rank them in order, we've got probably yellow would be the lowest because R is lower than the others. Then we have orange, which would be R sine theta, because we have this angle here for our orange that we have to take into account. And then we would have the blue dot with the longest radius and sine of 90, which is just 1, so we don't decrease that at all. So if we go back over, blue is going to have the greatest one, and blue is dot number 2. So 2 actually has the greatest torque on that problem.